And I need to go to my piece of paper in the beginning. So let me try to do that. Let's see if I can. Then I need to pin it. Okay. So what are we talking about? So real roots.
Mel, could you move it a little bit closer so that way it's not blurry or something? We tried that last time and it worked out.
Real roots of polynomials. So just to start with something unrelated to this, but where I had asked about quantifier elimination, which I don't understand, but what I know is the world's simplest example is if you take the statement, there exists an x such that x squared plus b plus c equals 0. That's equivalent to the statement where you've eliminated the quantifier, and x real is b squared minus 4ac greater than or equal to 0. So these two statements are equivalent, but here there's no quantifier, which is interesting.
No, we can't see the right side of your paper.
Well,
it's in focus, but we can't see it.
Right. How's that?
There it is. We can see everything but the 0.
Guys, you want everything, or to be precise, you want nothing. Yeah. So here's a mathematical statement, and here's an equivalent statement with no more quantifier. It's gone. It's been eliminated. Anyway, the question is, I'll start with, so everything I'm saying is classical. Classical means some of it was known in the 17th century. Thing was known by the 19th century. And the question is, given a polynomial with real coefficients, find the real root, or if that's too hard, find the number of real roots with or without multiplicities. So there was a British mathematician named Harriot, who was perhaps, at least he's often considered, the most distinguished British mathematician before Newton. And he did many things. And he wrote a book, but he didn't publish the book when he was alive. After he died, someone published the book for him, except that there part of it that the editor couldn't understand, so he just left them out. And it wasn't until I don't know, 20 or 30 years ago, that some people who were scholars of the history of mathematics actually went through his papers and put together, it seems to have been his text. And so there's some dispute in the history of mathematics whether it was Harriot or Descartes who first wrote down what is sometimes called, at least a version of Descartes' law of signs or rule of signs. And the way Descartes stated this, and it's easy to look up because Descartes' book on geometry, which if you look at it, it starts on page 278. And you might, why does he write a book that starts on page 273? And it's because he didn't write a book that started on page 273. There's the famous work in philosophy called The Meditations of Descartes. And at the end of his meditation, he adds several sections, one of which is on mathematics. And the mathematical geometry starts on page 273. I wrote in French, then it was translated into Latin so everyone could read it. And it's now available in English by my favorite publisher, Dover. So for relatively zero money, you can read Descartes' geometry, and it's quite interesting. So what Descartes says is that it's the following theorem: the number. So this is actually what Descartes writes: the number of positive roots of a polynomial. These are all polynomials with real coefficients. Is at most the number of sign changes of the coefficients. So what it means is if you have a polynomial like x to the 10th minus 9x to the 8th plus 3x squared plus x minus 5. So there's some coefficients, there's some powers of x you don't see. You don't care about them. You only care about the non-zero coefficients. And if you look at the sequence of non-zero coefficients, it's 1 minus 9, 3, 1, minus 5. It's this sequence. And in this sequence, there are three sign changes: plus to minus, minus to plus, and plus again to minus. So, and all one really cares about is the sign. So you can, from the point of view of Descartes' theorem, you just write a plus or minus 1. And you're looking at the number of sign changes. And there are three sign changes. So for this polynomial, if I write v of f is c, this polynomial of degree 10 has at most 3 roots, and I should say this is count multiplicity. So the number of positive, the number counting multiplicity is in most 3. Now, Descartes did not give a proof. One reads that Newton mentions this somewhere in his writings, also without a proof. People say, well, it's because Newton was so smart, it was too obvious for him to write down anything. But the first real proof is due to Gauss. And Gauss actually states a stronger version of the theorem, because to say that there are 3 sign changes according to Descartes means there are at most 3 positive roots, but there could be 0. Right? And in Gauss proof, Gauss says the number of positive real counting multiplicity is the number of sign change of number of positive real roots of this polynomial f of x. It just says f of x over here. F of x is the number of sign changes v of f minus an even integer. So this is really much stronger because, if v of f is 3, as it was in the example we saw, the number of positive roots either 3 or 1, right? the only number that you can get from 3 by subtracting an even integer is 1. So that means there's at least one root, which is something one did know from Descartes' statement. And Gauss's paper is less than 4 pages long. It's written in German. I can read German, and I could understand the first 3 of the 4 pages, and I couldn't figure out the. So I thought, well, maybe my German, at least my 19th, 18th century German, isn't as good as I thought. So I sent it to a friend of mine in Germany, and I said, could you please translate just the 4th page of this paper, because I can't figure it out. And he translated it and sent it back, and it was essentially the same as my translation, which just means I can't figure it out. On the other hand, you don't need it. And I'm actually going to give a proof, which is more or less, the first half releases Gauss's proof, and the second half replaces what I can't understand by a statement which is 100%. This is Descartes' theorem. Now, so there is a subject which I never studied, because old as I am, I'm still too young. But there's a subject that it used to be taught in colleges everywhere called theory of equations. And in a course in the theory of equations, 3 of the basic theorems were Descartes, a theorem of Boudin and Fourier, and a theorem of Storm. And in fact, one of the best books on this subject is a book written about 100 years ago by Leonard Eugene Dixon called Theory of Equations. And I've looked at other books that which discuss this, and they all say, but the only really correct proofs are what you find in Leonard Eugene Dixon from 1920 or so. But in any case, this is Descartes' theorem. Now, there's another way you could state Descartes' theorem, which is the following. So if you have a polynomial, which I'll make it monic, I don't lose any information if it's monic. Also, if you're looking for positive roots, you can, it's easy to tell if a polynomial has a 0 and what its multiplicity is. So if the lowest term is like x to the k times something, divide by x to the k. So I can always assume that my polynomial is monic and the constant term is non-zero. It's not, it just makes it easier at some point. Anyway, this is my polynomial, and what Descartes does, I'll write this as an, but even though an, what Descartes does, he looks at this sequence. And he's looking for sign changes where you ignore all the 0 terms. Now, someone was mentioning Taylor's theorem. So if I remember correctly, A0 is f of 0, right? And A1, I think, is f prime of 1. And in general, A sub k is something like k factorial times the k of 0. A1 is f prime 0. A sub k is k factorial times the k derivative evaluated as 0. So this sequence can also be written as the sequence f of 0, f prime of 0, f to the n minus second of 0, fn of 0. It's just the sequence of the function and its first n derivatives evaluated at 0. And these numbers only differ by a factorial. So in terms of the plus or minus signs, the sign sequences are the same. So one could say that you take a polynomial f of x, you evaluate the Taylor coefficients at 0, and the number of sign changes is the number of positive roots minus some easier. Okay. So Boudin and then later Fourier took this observation and they made the following statement, or proved the following theorem. So this is Boudin Fourier. I should have written polynomial, maybe. Well, I'll write it. I've been writing it. So the number of not positive roots, the number of roots of f of x in the interval, let's say from u to v, is the number of sign changes. I apologize for my illegible writing here. The number of sign changes when you take f of u, f prime of u, f double prime of u up to the nth derivative. So this is sequence. Ignore whatever terms might be zero and the number of sign changes minus the number of sign changes in the sequence where you evaluate at the right point v. Okay. So the number of roots is this minus perhaps some even. Okay. Which, by the way, is really curious because it tells you if you take a polynomial and you evaluate and you look at these numbers at u and v, as you move to the right, the number of sign changes only gets bigger because this minus this can't be negative, right? So, right, isn't that kind of a curious fact? And it's not hard to see that Descartes' theorem is an immediate corollary of this, because in general, if you have a polynomial f of x equals x to the n a n minus 1 to the n minus 1 plus a1 x plus a0, and you let m be the sum of the absolute values of the coefficients, then it's sort of an exercise in pre-calculus that if f of d 0, then d absolute value is at most the maximum of 1 and this number. So there's a very simple upper bound and lower bound for where a 0 can occur. So if you take this Boudin-Fourier theorem and you let u equal 0 and v equal this number m, that will tell you how many roots there are between 0 and m, but that will be all the positive roots. So Descartes' theorem follows from Boudin-Fourier very simply. Now, maybe 100 years later, there is the fifth theorem of Sturm, which says the following. So Sturm's theorem gives a precise count. So in Sturm's theorem, you have the following statement. So you have a polynomial of x, and for any numbers a and b, a less than b, the number of distinct roots of f of x, distinct roots d, with d between a and b is exactly the number of sign changes of something. I say fill in the box because something takes that to write down, and I have that printed out somewhere. So this is the number of roots, not counting multiplicity. So it's the number of distinct roots. This is Sturm's theorem. Now, I have no reason. I have no idea why I'm interested in all of this. At one time, something led it to me, and then I just got interested in it. But I'm also interested in something I know absolutely zero about, but hope to figure out in the next couple of weeks if I can. From Sturm's theorem, there is a variant due to Alfred Tarsky. Tarsky was important logician, came to the United States in the 30s or so, I assume, and I think he was at Berkeley. So there's a Sturm-Tarsky theorem, which is a refinement, perhaps, of this polynomial theorem of Sturm. And Tarsky used this to prove what one might call Tarsky's theorem, which said real numbers are decidable. Let's see. So this can mean lots of things. I'll give you a simple-minded version of what it means. So if you have a polynomial f of x with integer coefficients, and you want to know if you can solve f of x equals 0 in z, the answer is sometimes you can and sometimes you can't. But in general, for all polynomials, you cannot. So this is Hilbert's 10th problem, which was reduced by
This is for polynomials with a lot of variables, though, right? If there's just one variable.
Yeah. No, f of x1 up to x of k. So if you take a polynomial and several variables with coefficients in z, you want to know the solution. And the answer is maybe there is and maybe there is, but there's no algorithm. So Martin Davis, Hill Putnam, Julia Robinson reduced the existence of a rhythm to some statement about whether an exponential relation is Diophantine, and more or less at the same time, Matyasevich and Gregory Chudnovsky proved that there is an exponential relation which is Diophantine, and therefore Hilbert's 10th problem is no solution. So, but the Tarsky result, which was extended by another guy at Berkeley named Seidenberg, so what's called the Tarsky-Seidenberg theorem, says something like the following. So I misstate it because I will misstate it. But I will give you what I think is legit is. There is an algorithm to decide if a polynomial f in, I don't know, m variables is a 0. Right? So over reals, the polynomial root problem is decidable. Okay, I think. So now we have a lot of logicians at the Graduate Center. And I wrote to one of them and I said, can you explain, or I have a question about this. And he said, well, truthfully, I don't really understand it, but my colleague so-and-so does. So I wrote to his colleague, another guy at the Grad Center, and I said, can you explain this? And he said, no, but this third guy also at the Grad Center understands this. So I wrote to him And he said, well, not really, but yeah. So, well, that
So
means
the proof is not undecidable, but incomprehensible.
no, it's not. So, but point is for me that what Tarsky under somehow was that could reduce the solvability of polynomials over the reals to an extension of Sturm's theorem. That's what I find really interesting. And I've been trying to find someone who can tell me something about the Sturm-Tarski theorem. It has to do, there's something called, so everyone knows what an algebraic set is, right? You take a set of polynomials and you look at their common zeros, and that's an algebraic set or an algebraic variety. If instead of taking just a set of polynomial equations, you take a set of polynomial equations and polynomial inequalities, then you have what's called a semi-algebraic set, in n dimensions. And the big theorem is somehow that if you project the semi-algebraic set down from let's say dimension n to dimension n minus one, the set that you get is still semi-algebraic. And somehow the crux of Tarski's decidability result. And the proof of that somehow uses Sturm's theorem. So if anyone can what I'm talking about and can explain it, that would be great. In any case, just find it really interesting that, Tarski's work now is probably 75 years old, right? I think he had proved this in the late 30s, maybe around 1940, when he was maybe still trying to stay alive in Poland. And he didn't actually publish a proof until after World War II had ended. But in any case, I find that quite interesting. Okay, so what I'm going to do is give, I want to show you Gauss's proof more or less of Descartes' theorem. And then I would also like to show you a proof of Sturm's theorem. Sturm's theorem is hard to prove. And I've looked at a lot of, but the best place by far is Werner Verden's Modern Algebra, right? This book is now about 80 years old. He gives a proof of Sturm's theorem, which is clear, beautiful, no bullshit. It's great. And somehow he has there's some questions about his behavior, World War II, but he did do a lot of good mathematics, and his algebra book is still perhaps the best algebra book there is. And almost every algebra book you look at, whether it's Lang or Dummett and whatever is Dummett and somebody, Dummett and Foote, everybody's table of contents is basically Van der Waerden's table of contents, only they throw in stuff. So the book is a lot fatter and weighs a lot more. Anyway, I think there are later editions of Van der Waerden's Modern Algebra, but the one I have on my shelf is the original one that was published in English. Published because the publisher was able to get the copyright under, what it was called, Van der Waerden's Algebra, right? This is the book. Yes, there was the Alien Properties Act in the United States. When World War II broke out, we passed a law called the Alien Properties Act, and we seized all German property in America. And that included copyrights. So a number of publishers were able to publish really good books, either in German or translate them into English. And they got the copyright by permission of the US government under the Alien Copyright Act. So Chelsea Publications, which has a lot of great books, got their start, I think, really by books they got under the Alien Properties Act. Okay, that's all. Interesting history for people who like history. This is Descartes' theorem. So the page of Gauss's paper I cannot understand can be thrown away by the following remark. Suppose I have a sequence let me just write it as, let's say, epsilon 1, epsilon 2, up to epsilon sub k. It's a sequence where epsilon I is plus or minus 1. And I want to know how many sign changes there are, right? A sign change means a 1 followed by a -1 or a -1 followed by a 1. Well, I mean, obviously, I can't tell you how many there are because I don't even know what k is, right? I mean, but what I can see is the following. If the starting and end points are the same, if this is a plus and this is a plus, or this is a minus and this is a minus, then the number of sign changes is even, right? Like if you go from a plus to a minus, you're going to need a plus to end up at a again, right? So if you start and end at the same sign, the number of sign changes is even. Epsilon is not equal to epsilon k. One's positive and one is negative. Then the number of sign changes is odd. Okay. So what is the difference between Descartes' theorem and Gauss's theorem? Descartes' theorem says the number of roots is at most the number of sign changes. Gauss's theorem is much better. The number of roots is the number of sign changes minus an even number. And you can get the even number just from this remark, okay? But of course, you need more than this because this is just a remark. So how do you get from polynomial to something? So this is what Gauss does in his paper. And I hope after I show you this, you will agree that Gauss really was a smart guy. All right. So suppose I have a polynomial, I'll call it g of x, which is x to the n dot 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 plus a sub k plus 1 x to the k plus 1 plus a sub k a plus a0. Okay. And I take this polynomial and I choose a number lambda that is positive. And I look at, actually, it makes no difference whatsoever, but I'm going to call this h. This is h. And I'm going to let g of x be equal to x minus lambda times h of x. Okay? So, and I want to figure out what is the coefficient. So, I mean, if you cannot teach this to your pre-calculus class, I mean, you can teach this to your calculus class. What is the coefficient of x to the k plus 1? So I have the coefficient is a sub k, because if I multiply this by x, I get a sub k, x to the k plus 1, minus lambda a sub k plus 1. And then the constant term at the end is minus lambda a naught. Okay? Now, so this is the coefficient of x to the k plus 1. Now, suppose there is a sign change at x to the k. So maybe, I mean, there are two cases, either maybe a sub k is positive and the first term before it that's non-zero is negative, or the other way around, but everything is symmetric. So suppose a sub k is, that means that a sub minus 1, if it's non-zero, it has to be negative. Sorry, a sub k plus 1. If it's non-zero, it has to be negative because there was a sign change, or it's zero. But in any case, a sub k plus 1 is than or equal to 0. Okay. So this is positive, lambda is positive, but a k plus 1 is less than 0. So a sub k minus lambda a sub k plus 1 is greater than or equal to a sub k, because this is non-negative, which is greater than 0. So if there's a sign change at x to the k, and a to the k has a positive coefficient, then x to the k plus 1, when I multiply by x minus lambda, also has a positive coefficient. And if ak were negative and there were a sign change, this would also be negative. Okay? So, okay. So let's think about that for a second. Here we have h of x, and at various places there's sign change. So somewhere you have a term a sub 1 x to the k1, where this is now negative. So this, let's say positive. I mean, it always starts positive because the leading coefficient is 1. So you have positive, and then you either have 0 or positive. The first time you hit a negative coefficient is here. This is negative. And then it's like negative for a while. And then you get to a point where you have another sign change. This becomes positive, and so forth. So if you look at the polynomial h of x, let's say there are sign changes, and the last sign change is k sub r x to the k sub r. Okay? So you have r sign changes here, here, and so forth up to here. Now, when you multiply by x minus lambda, this becomes x to the plus 1, which is positive. Here we get a coefficient x to the k1 plus 1. Here you have times something. And here this is as x to the k2 plus 1, x to the sub r plus 1. This is positive. This is negative. So you have just one sign change here to here. And then this is negative and this positive, but this is positive. So you have another sign change. So if you look at h minus lambda times this is g of x times h of x, right? That's this product. I have, if I just look at where the sign changes occurred in h, and I shift those powers of x by 1, I get sign changes in this new polynomial. There might be some other sign changes in here, and here, and here. I don't know, but in any case, there are at least these r sign changes. And actually, we know there's at least one more. This is last sign change. So for example, if this is positive, all these coefficients are positive. If this is negative, all these coefficients are negative. But what's the constant term in x minus lambda times h of x? Minus lambda naught. So multiplying by x minus lambda. So whatever the sign of a naught is, lambda is positive, so this has the opposite sign. So from here to here, we have one more sign change. So the number of sign changes is at least the number of sign changes in the original polynomial plus 1, right? But of course, it might be more than that, right? Because you know, I have no idea what's going on in here in all these places. But as I go from x to the n plus 1 to x to the k1 plus 1, as I go from here to here, how many sign changes are there? This is positive, this is negative. So the total number of sign changes to be odd. This is one of them. So it's 1 odd. Odd means plus an even number. So I have some even number of sign changes in here, plus this guy. And in each of these gaps, I have, in addition to the R changes, sign change, I have plus some even number, plus 1. So if h of x has R sign changes and lambda is positive, then g of x, which is x minus lambda h of x, has how many sign changes? R plus the one we saw from the constant term plus some even number. Could be 0, but it's either 0 or a positive even integer. So if you take a polynomial h of x, you multiply it by your factor h minus lambda, and lambda is positive, the number of sign changes goes up by an odd integer. Okay? Okay, now that's Gauss's brilliant idea, right? I mean, you know he's smart because he could do this in his high school algebra. You know, probably even in century Brunswick or wherever he was in Germany, it was high school algebra. So how do we make Descartes' theorem from this? Okay, well, we get it as follows. We started with a polynomial f of x. F of x has positive roots, negative roots, and complex roots. Okay? Everybody happy with that? And the complex roots, of course, occur in conjugate pairs, because our polynomial has real coefficients. So suppose I let h of x be the product of x lambda sub I, where minus lambda. So the positive root, I'll call the negative roots. Sorry. The negative roots are minus lambda to the 2, I minus lambda sub p. And the complex roots are, I don't know, I'm running out of letters here. What can I use? U sub t plus v sub ti. Okay? So I want to take the product of x minus d, where d is a negative root, and the product of x minus d, where d is a complex non-real root. Okay, okay. So this is a product. The negative roots are minus lambda, so the product of things that look like x plus lambda sub I. And since these roots occur in complex conjugate pairs, these factors look like x squared minus 2u sub t x plus u sub t squared plus v squared, right? So if I take the product of the negative roots, so I'm looking at x minus the root, negative roots and the complex roots. And all I have to say is that this is positive and this is positive. I don't care what happens when I multiply this out. All I know is I get x to some power plus garbage plus some constant term which is a positive number, because I'm multiplying the positive lambdas in these sums of squares. So this function, which is the product of all the non-positive roots, has a leading coefficient that's positive, a constant term that's positive. How many changes of sign are there? Positive to positive means there's an even number of changes in this polynomial. So what I've just said is I have some polynomial of x, and I let h of x be the product of x minus alpha. I'm sorry, I can't. Whether alpha is a negative root of f or alpha is a complex non-real root of f. And whatever this is a polynomial with an even number of sign changes, right? Because you start with a plus sign, you end with a plus sign. The number of sign changes, plus to minus to plus to minus, has to be even. Because if you go to minus, you got to come back to plus. Okay, so that's my polynomial x. And what is f of x? F of x, this is a polynomial, so it's the product over all the roots. So it's h of x is the product over the non-positive roots times product x minus lambda, where lambda greater than 0 is a positive root. So how do I get from h of x to f of x? I start with h of x. This has, let's say it has, I don't know, R0 sign changes. And multiply it by x minus lambda. Lambda is a positive root, x minus lambda 1. I get something with how many, and the number of sign changes is even, 2 are not. So how many sign changes will this polynomial have? It'll have the original number plus an even number plus 1. You get one more. Another root, or if the root lambda has multiplicity more than 1, you can take it again. Minus lambda 2, x minus lambda 1, x. The number of sign changes will be the number you started with plus an even number plus 1. Write this as, I'll call this 2s2 plus 2. And then take this and multiply it by x minus lambda 3. So I have how many sign changes? The number I started with plus some even number plus 1. So even and even, it's like 2s3 plus 3. And if f has r positive roots, has L positive roots, then after I've multiplied by all L of these factors, I see that f of x has how many? It has even number plus L sign changes. So this is the number of sign changes. This minus an even number is the number of roots. That is my version, at least, of Gauss's proof of Descartes' theorem. All right? It is very simple. All right? I still wish I knew what Gauss wrote on the last page of his paper. He has I just found it like gibberish. And since it was Gauss, I assume it is not gibberish. But if you use this observation that if you're just counting changes of plus to minus to plus to minus, if you started a plus and ended a plus, you have to have changed things an even number of times. If you started a plus and ended a minus, you had to have changed things an odd number. So that's Descartes' theorem. Okay.
Could you share one of these translations of Gauss?
Yeah, sure. I can say what I wrote out. But I would just ignore the last page because I just can't figure out what he said. And I actually did. I translated it myself. Sent it to this friend of mine in German, translated it. But he said, this is not my subject. I don't understand any of it. But it was still, it's a translation. And yeah, sure. I'll send it to you. Okay. So all of this was supposed to be, of course, the first 5 minutes of my talk. And I had, let's see, where the hell is it? Yeah. I don't know. Can you see this? What says sign changes in real roots of polynomials? Maybe not. I'll get rid of it.
Could you highlight where you're talking about? We could see the page of tech.
Oh, okay. That's what I wanted. Share screen. Text not file. So is this visible?
Yes, this is the PDF.
Right, okay, so I had actually written out the proof of Descartes' theorem, and then I wanted to give van der Waals' proof of Sturm's theorem. Van der Waals starts off by saying this, and I thought this was incredibly modern. Of course, his book is modern algebra, but it's not modern. It's modern art means art from the 19th century and early 20th maybe. Modern algebra means algebra from the 9th century, early 20th century. But he says, we now turn to the computation of the real root polynomial f of x. By computation, we mean in accordance with the definition of real numbers, an arbitrarily close approximation of rational numbers. And he makes the point, of course, that Sturm's theorem doesn't just tell you how many roots there are, but it tells you to any degree of precision you want what they are. So somewhere I put in an example. And everything he does, it's based on what he calls Weierstrass's No-Stellensatz, which simply says if you have a continuous function from A to B, a polynomial, it doesn't even matter, a continuous function from A to B, if it's negative at A and it's positive at B, then it's zero somewhere in the middle. That's all he uses. Why Weierstrass's name is attached to it, I don't know. But it's also the case, since this is all you need, if you go to real closed field, you can do practically everything there that you can do in the reals. So Sturm's theorem says yeah, so you build a sequence of polynomials. So it's sort of a modified Euclidean algorithm. You take a polynomial f of x with real coefficients. You let f0 be f and f1 be the derivative of f, which, it's the derivative. So it's a purely algebraic thing, right? The derivative of a polynomial. And then you divide f0 by f1. You get a quotient and a remainder. but instead of writing the remainder, you let f2 be minus r2. So you write the division algorithm with a negative remainder like this, right? Negative in quotes, because of course these are polynomials. And then you take f1 divided by f2, you get a remainder in the chain, you change the sign. So you end up with a sequence of equations like this, and it's the Euclidean algorithm for polynomials. So the degrees of the remainder polynomials are strictly decreasing, and it terminates at some point, right? You have this sequence of the polynomials, and if you look at this sequence, evaluate it at A, you get a sequence of real numbers, which has a certain number of sign changes. And if you evaluate B, you get a sequence of real numbers, which has a certain number of sign changes. And the number of sign changes at A, number of sign changes at B is exactly equal to, not equal to minus an even number, is exactly equal to the number of distinct roots between A and B, not counting multiplicity. So this is Sturm's theorem. By this variation V sub f, that just means the number of sign changes in that sequence, and this is multiplicity spelled wrong, but yeah. So here I put it in an example. So obviously I'm not going to prove Gauss's theorem, or the Sturm theorem. Here's a quintic polynomial. This is the polynomial. This, I think, is the derivative. I have to do this by hand because I don't know how to. By this, this is the quotient, and this is the so this is f0, this is f1, and minus this is f2. And then I take this and divide by this funny looking quotient, this remainder. And then it stops. No, you can't go on. All right, so I have my original polynomial, this derivative, f2 and f3. So I want to evaluate this at particular values of x and look at the number of sign changes. Now, if you take this polynomial, the coefficients are 1, minus 6, and 3. If I take the sum of their absolute values, it's 10. So you know from high school algebra that every real root of this polynomial is between minus 10 and plus 10. So if I evaluate this sequence at minus 10, I get these four numbers, minus, plus, and here I just put it the same table down, but with minus and plus signs instead. Minus, plus, minus, plus. There are three changes, minus to plus, to minus, minus to plus. If I evaluate sequence at x equal 10, these numbers, and you see they're all positive, so the number of sign changes is 0. So this v of 10, v of minus 10, minus v of 0 is 3. So that says that the polynomial has 3 roots, not counting the multiplicity. And you might want to know, where are they? So I also evaluate this at minus 2, minus 1, 0, 1, and 2. At minus 2, it's still 3. That means there's no root from minus 10 to 2. At minus 1, it's 2. 3 minus 2 is 1. So there is a root between minus 2 and minus 1. Minus 1 to 0, same number, difference is 0, no root. Between 0 and 1, there's a root. Between 1 and 2, there's a root. So this tells you where the roots are, where the 3 roots are, at least in unit intervals. Well, but if I want to make it more precise, evaluate this, for example, at a half. And that'll tell me whether my I know is between 0 and 1 is between 0.5 or a half and 1. But this is Sturm's theorem. I mean, there's a proof in Lang algebra book. It's horrible to understand. There's a proof in Dummett and Foote, which is comparably to understand. The proof in van der Waerden is clean, simple, elegant, no bullshit. It's lovely. I mean, smart guy. I mean, of course, Lang and Dummett and Foote were smart guys too, but Van der Waerden writes better, at least according to my taste. So,
Elvin, I like to remind you that in the title page of the translation, it indicates clearly that in part the development from lectures of Emil Artin and Noether. So,
oh, absolutely.
knowing
No, no.
the style.
It's, I mean, that's everyone, right? This is understood by everyone, I think I said it maybe. But Emil Noether and Emil Artin were lecturing and out the creators of the subject. And Van der Waerden is basically taking, I guess, I don't know whether he went to his lectures, whatever, but based on the Noether Artin lectures. In terms of, I mean, just the way Lang probably didn't prove anything in Lang's algebra, but as an expositor, Van der Waerden is very clear.
I'd say that some of the elegance in Van der Waerden goes back to Artin and Noether.
Yes, probably. I mean, they both were, especially Artin was an extremely elegant writer, but and Artin was also Lang's thesis advisor, I think, at Princeton, as Artin was also Tate's advisor.
But I suspect
the
Lang
problem
was
with
more.
Artin's was Artin's lectures were like a Chinese meal. It seemed beautiful when you were there, but an hour later you forgot everything. Van der Waerden took notes.
Yeah.
Yeah.
Okay.
Also, there's a proof of Descartes theorem in Weber's algebra, which, as I recall, is also pretty clear.
Yeah. Anyway,
So,
Oh.
right. Enough. It's hard work here. I would like to find a logician somewhere, but I actually, probably Kevin, your former colleague, who maybe he's at Notre Dame now, probably knew this, but he seemed to know. Well, he was more set theory than logic, but he seemed to know a lot of this kind of stuff.
I miss him.
Oh, yeah. Okay. Let's see what's in the chat. Yeah. I think I was in the Graduate Center library. There's like a 5th or 6th edition of Van der Waerden in English. And the name was changed, as someone pointed out, to algebra. But at one point, Van der Waerden's algebra was like Samuel's economics. That is, it was the book that everyone studied to learn algebra.
It's got a lot of gems in there. For example, the discussion of Hensel's lemma is the one that I always presented in my courses. When it came to Galois theory, there are excellent examples in Van der Waerden, but I found it more useful to go back to Artin's notes on Galois theory.
Yeah. But what I found, the trouble with Artin's notes on Galois theory is Dick just said they're extremely beautiful. They're too beautiful, and like at the end, it's like you didn't get your hands dirty. It's like it's so elegant.
Yeah, you got to go back to the recipe and read it carefully.
Yeah. And what people say of Van der Waerden's treatment of algebra is that it is, well, in many places, very constructive. So there are, in some sense, algorithms or ways of solving things that are useful. But
so I don't have a copy of Van der Waerden. Is it one of those books where I should get like an early edition, or I should get the latest, most revised thing? Did it get worse in the revisions?
I've never looked at. when I was a graduate student in somewhere in the 19th century or so, I bought Van der Waerden, and it's 2 volumes. I obviously got it at no, I think they each cost $6 hardcover. And I've never really looked or even held the more recent editions, so I don't know anything about them.
Kevin, can you hear me? It is David.
Yes, I hear you.
Okay, Mel, do you have Van der Waerden book in front of you? Hello. When it was published, can you look at the front page?
Yeah. So the first English edition was 1949.
Okay, very good. On the front page, it would be written, printed by permission of custodian of alien property of the United States.
Exactly, the alien property
Okay,
custodian.
so what US government did when Nazis started the war, they basically totally reprinted all Springer at $1 a piece. This is exactly edition, Kevin, you want to buy. They are old and many are sold online, discarded by the libraries, because it contains the only difference between the latest Springer piece and that there are some pieces missing on real fields and so on. And about 20 years ago, I had a conversation with, may he rest in peace, Hirzebruch, and I said, and why the fuck in the new edition they removed pieces? And Hirzebruch did not believe me, so when we looked, I pointed it out to him, and a year later, Springer put it back. So my advice to save the money and have, I would say, a piece of history, it makes sense to buy the thing published by the orders of custodian of alien property of United States. And by the way, it is the only edition which I have in my library.
Yeah, me too.
Yeah. That's good information. I've been looking for some German books, but I am not willing to pay the high prices in some of the internet offerings. So I'll look for the.
Look, if you look at the old book, but it was a massive operation. Why Nazi has to charge through the roof for Courant and Hilbert and all whatever other things, when U.S. government just take, photographically reproduce it and,
Yeah, it's also interesting, yeah.
By the way, the Office of Custodian of Alien Property was never shut down. It sits in the Treasury Department waiting to be used in the future, maybe in the near future.
David, let me ask you a technical question about copyrights. If when I first published my book on algebraic curves, the publisher, Cambridge University Press, came back and said, "Do you want to make a digital copy?" And I said, "No, it should never be sold under a digital copy." But I recently discovered that the Internet Archive has digitized the book. And so I'm wondering, at one point or another, someone has, the book is still under my own rights, at least for 70 years, as I understand the American law. But someone must have obviously given the Internet Archive the rights to make a digital copy.
No, they don't have
make
the
it free.
rights to make a digital copy. because your original tape terms of copyright says reproduced on any media, electrical, mechanical, or otherwise. So if actually for example, Disney use it, everybody use it, songwriter use it, you, when the book was first published, when your book was first published?
92 or so.
Okay, fine. So if you renew your copyright, and this is not a complicated matter, you can look it up online or pay something very modest for consultation to copyright lawyer, you have a full copyright, electronic or otherwise, for 75 years since the date of publication.
Right.
So you can compute till when, and then if somebody puts a digital copy on internet, you send them a letter saying, I am the copyright holder, please desist and remove this or else. It doesn't mean that you will sue them, but if they don't do it, there is a, you know, because there were cases when people who did this were sued and lost to the tune of tens of thousands of dollars. So just research it a little. But they have no right to put, you know. By the way, the copyright was invented for many good reasons, and one of them I will tell you, you will laugh. You see, Mark Twain was a very popular writer all over the world, particularly English-speaking world. And when he published his books, the Brits would reprint them and pay him no copyright. Not at all. So he really was in a poor house. And you know, he has a house in Connecticut where he lived. He married well, but he was very poor. So one night, it was a stormy night, and a man knocked at his door. So Mark Twain opened and said, how can I help you? And the guy who was shocked said, I am here to help you. My name is J.P. Morgan. Okay, so they became friends, and actually Morgan paid for massive copyright suit, after which the Brits had to pay American authors and Mark Twain, you know. But he really felt very bad, so he came in the evening to explain to Mark Twain how it is done. And Mark Twain was not exactly extremely friendly. You know, yes, I am J.P. Morgan. I am here to help you. Please, could I come?
Yeah. No, it's interesting. I have to learn a little bit more, because my understanding was a few years back, someone made a Chinese translation of my book, and they wrote back asking for permission to print it. And I asked the Cambridge University Press whether that, you know, what was going on. I said, no way, they cannot do that. We still hold the copyright even in China.
I assure you that they reprinted it.
I'm not so sure, yeah.
The Internet Archive just takes uploads by whoever, and it only comes down after an author challenges.
Correct.
There, so.
Yeah, I remember a couple of years ago, or perhaps a little bit more, the translations of Thomas Mann's were put on the Internet Archive, but then the original holder of the copyright in Germany sued. They won, so they were removed, basically.
My favorite story about copyright was Amazon, George Orwell in 1984, the book. So Amazon was selling 1984, and copyright for this is owned by a state of George Orwell. Okay? So they sued, and Amazon did incredible thing, which they had no right to do. You probably don't know, but when you buy a Kindle book, if you read the legalese, you actually don't own the book. You paid the money, but Amazon owns and totally controls whether you will look at a book. So when the estate of George Orwell won, the Amazon removed the text of 1984 in 1984 style from millions of people who had this on their Kindle. And I don't have to tell you what kind of scandal followed it.
Well, it's tricky, Amazon, yeah.
Okay. Good to see everyone. David,
Well,
thank
many,
you.
many thanks. Many, many thanks. It's a lot of fun.
Josiah, we'll
been-
talk about
it was a-
next week.
Okay.
But not now, because
Yeah,
I
I'll
have
send you an
to
email.
also.
All right. Take care.
Okay.
All right.
Bye, all.
See you guys.
Right.
It was an enjoyable hour.
Yes. Very nice.
You will.
Interesting.
Forget about learning, have fun.
Mhm.